whatever that object may be, X never belongs to the empty set. That's what empty set is. It doesn't have anything. So this hypothesis is false. Now, regardless of what the conclusion is, the implication is vacuously true. That means actually this is a valid implication, and that's why we have a function. It is somewhat strange, but this is known as the empty function. It doesn't do anything. It just exists because we have vacuous truth, and the condition is true here. Vacuously means it never happens, but nonetheless it's true. You can also think of it in another way. For a function to be like this, I mean for a relation to not be a function from the empty set to X, there must be at least one element in the empty set that is not related, that does not have an output. Such an element cannot be found because the empty set is empty. Or there is some element in the empty set which has more than one output. That such an element also cannot be found because the set is empty. So that's why this function exists. It's more of an existence issue than what the function does to any element of because the empty set, because the empty set doesn't have anything. So in that sense, this is a function. And it's known as the empty function. Instead of explaining this much, the author, however, writes, which also has the same meaning, although one has to think of it for some time to understand that what he writes here or what he says here has the same meaning that we have just now discussed. What he says is this: since the empty set does not have any element the empty function does not need to specify what it does to every input, because there is no input. But just like the empty set is a set, the empty function is a function. Albeit not a particularly interesting one. Okay. Mathematics is about truth. It's not about whether something is interesting to you. Of course, you have to search for beautiful results, but that does not make this false. It exists, the empty function. Note that because of definition 337, means definition of equality of two functions, there exists exactly one empty function from the empty set into X for every given set X, Y. Why cannot there be two empty functions from the empty set into X? This I leave to you to you convince yourself why there has to be, there is one function that we have seen just now because of that vacuous truth of the implication. But why only one? You convince yourself that that is the case, and to do that you consider two empty functions and use this definition 337 of equality of two functions to conclude that they are actually equal. Okay, so that I leave to you. Now after this, here they mention that equality obeys the usual axiom. Equality of functions obeys the usual axioms means reflexivity, symmetry, transitivity, and the fact that it satisfies the axiom of substitution. So those things are true for this concept of equality. And that is the first exercise. Okay. Now after this we come to another definition of something very important known as composition of two functions. It's important in analysis, but it's even more important in algebra. We will see this when we study group theory. So this is definition 3310. Composition of functions. Let f from x into y and g from y to z be two functions where we are drawing your attention to this fact that the domain of G equals the range of F. This is important because otherwise we don't define composition. The domain of G is equal to the range of F. We define the composition of F and G written as GOF. O actually it's not O, it's a small circle. G circle F to be the function with domain X, range Z, and what have I written? We define the composition of f and g written like this to be the function with domain x, range z, and is given explicitly Okay, so here what have we written? You see, this is my set X, this is Y, and this is another set Z. Note that these sets, some of them may or may not be equal to one another. Okay, we are not considering those things. We are generally taking three sets. X may be equal to Y also. That does not matter. Now, f is a function from x into y, and g is a function from y into z. So now, the domain of g is y, which is also the range of f, and in that case, we define the composition of f and g to be a new function, whose domain is x and range is y, and it is defined explicitly using this formula. What it does, you have any element x in the domain, it sends x to this element gfx, because you see f sends x onto fx. Now fx is again an element in the domain of g. So it will have a G output, and that G output is this. So at once the composition sends this X onto that G output of Fx. So that is the composition. Now there are, I think, examples illustrating this here. But before that, there are some other things. When the domain of G is not equal to the range of F. Suppose these two sets are not equal, turn out to be not equal. B we leave the composition undefined. In that case, we don't define any composition. It's easy to see that composition obeys the axiom of substitution. And that is also in that same exercise, first exercise. Both this and the fact that is it in the same exercise? I don't know. 3, 3, 1. Okay, we will see. This may not be 3, 3, 1. Okay. In fact, let me quickly see whether this is the same thing or not. Just give me a moment. composition. It's written exercise 331. Okay, we will see. Now we look at an example that illustrates this concept. So here let f be a function with domain and range both a set of natural numbers, be the function that sends every natural number n onto twice its value. And what is g? G is another function. And let g also has n as its domain and range. Be the function which sends n onto n plus 3. Then G composition F, or let me just write what it does to the input n. Let me just write that. You see, first of all we will apply f to n. So that will take n to 2n, and then to 2n we apply g, that which sends 2n onto 2n plus 3. So that means we have this. Note that in this case the domain of g is n, the range of f is n. They are equal. So this composition is meaningful. It can be defined. But you also see that the domain of f is also equal to the range of g. So we can define another composition, f composition g, which sends first n onto gn, that means n plus 3, and then n plus 3 gets sent onto twice its value, that is 2 times n plus 3, or 2n plus 6. I think it's better to write, since this has just been introduced, it's better to write this thing in detail. G of fn is 2n. So g of 2n is 2n plus 3, and f composition gn is equal to f of gn. So that is f of n plus 3, which is 2 times n plus 3, that is equal to 2n plus 6 for all natural numbers n. So G composition f and f composition G are not equal. They are different as functions. For instance, G composition f of 1, what does it give us? If I take n equal to 1, then here I get 5. But f composition G at that same input 1, gives me 8. So since at the input 1 they differ, so that's why by definition 337 of equality of two functions, they are not equal. In other words, composition of functions is not commutative So composition, you see, after all, composition is an operation between two functions, right? It takes two functions f and g and gives you another function or g composition f. Just like you take two numbers and you add them, it's like that. It takes two things and gives you a third thing. It's a binary operation. But this in general is not true. However, this is true. That's why composition of functions is not commutative. In spite of this lack of commutativity, it's associative. However, composition is still associative, and that is the next result. This is lemma 3312, and the title is just that: composition is associative. Let f from x to y, g from y to z, and h from z to u be three functions. Then H composition G composition F, if you bracket them in this way, that is equal to H composition G composition F. That is the associativity. We now prove this. The proof is very easy. It's nothing difficult. Okay. Note that the domain of G equals the range of f. Domain of G is y, range of f is also y. So the composition G composition f, which is a function with domain x and range z. Look carefully, the intermediate set vanishes. The domain is the domain of f, the range is the range of G. Composition makes sense. Makes sense or exists. G composition f is a function with domain x and range z. Now, okay, now the domain of H, equals the range of G composition F. The domain of H is Z, range of G composition F is also Z. So, this composition, H composition G composition F, exists. And what is the domain of this composition, this larger one? It is the domain of this one, I mean the inner one or the rightmost one, and the range of the left one. That is, domain is X and range is U. That is, you start from X, the intermediate set Z vanishes and you end up at U. So that means this is a function with domain X and range U. Oh, I have to write it exists. Similarly, shall I write similarly or let's just argue? Because it may be somewhat confusing at first. Similarly, okay, now we have to form the function H composition G. Similarly, the domain of H equals the range of G. Both are Z. Domain of H is Z, range of G is Z. So, the composition H composition G, and it will take us from Y to U. The intermediate set Z vanishes. Y to U exists. Also, the domain of F, domain of H composition G equals the range of F, and they are both Y. Domain of H composition G is Y, range of F is Y. So, the composition H composition G composition F, and what will its domain be? We will come from X to Y and then from Y to U. So its domain is X, intermediate Y vanishes, and range is U. This exists. Now you look at these two functions. First of all, they exist. The second thing is that they both have the same domain and same range. Thus, G composition F, I have to write H first, right? H composition G composition F, and this have the same domain and same range. So this is the first condition for two functions to be equal. We have to then check that they map the same input onto the same output. Next, for any x in the domain, we have the first one or second one, it does not matter, but let's take this one first. H composition, G composition, F, X. By definition, this is the composition of these two functions. One is H and the other is G composition F. So, by definition, that is H value of G composition, F value of X. Now, inside we then apply the definition of this composition, thereby we get this. Now look at this. This can also be written like H composition G of F of X. Okay, by definition of composition. And finally, this equals composition F X. Hence, by definition 337 of equality of functions, and that's how we get the proof. Okay, after this there is an important remark. This remark addresses the confusion in the direction of composition. You see, when we have f from x into y and g from y into z, ideally, I mean just simply thinking of it, the composition should have looked like this. First we are applying f, then g. We are using f and then we are using g. However, instead of this, we write this. Why? That's because we write the input on the right side of the function or the function on the left side of the input. So that's why when we apply this on x, f has to be applied first. And then on the result we have to apply g. That's why the order has to be changed, and this creates confusion for the first time when we see this. Now if we decide to write function on the right side instead of on the left side like this, we would write something like this, xf. This also has the same meaning. It's the output of f when the input is x. But in this case, if we write like this, the composition will be written like this. Because now you can apply f first and then g. This is used sometimes in algebra, but not in many other places. There are even more different notations for this whole thing. Some people also write xf, but these things are not that popular and they create more confusion than clarity. Although in Herstein's topics in algebra, Herstein sometimes uses this, but at the same time sometimes he uses this, which it may have some advantages, but it creates a lot of confusion. So this remark is about that. So what it says is this, basically this thing what we have said just now, but in some sentences. So it says, note that G appears to the left of F. Yes. In the composition, G composition F. The composition applies the rightmost function, that is in this case F, first to the input before applying G. This happens